Hello everyone. This is the last topic of the unit second of subject pharmaceutical organic chemistry third. In this topic, we are going to discuss about stereoisomerism in biphenyl compounds, that is also known as atropisomerism, and we will also look upon the conditions under which biphenyl compounds exhibit optical activity. In next section of this discussion, we would discuss about stereospecific and stereoselective reactions. We will also focus on the differences between stereospecific and stereoselective reactions. Stereoisomerism in biphenyl compounds is a typical example of conformational isomerism. Biphenyl compounds are now see what is happening. These bulky groups like A prime, B prime are introduced around this carbon-carbon single bond at the ortho position of the biphenyl nucleus. Introduction of these substituents result in the steric hindrance. This steric hindrance generate restricted rotation along this bond, and as a result of this restricted rotation, atropisomers are obtained. So atropisomers are stereoisomers that are resulting from hindered rotation about single bond where the steric strain barrier to rotation is high to allow for the isolation of the conformers. The question arises why these atropisomers are enantiomer. Yes, if substituents are different, a chiral molecule exists and these atropisomers are the enantiomers. Now if we look upon this word atropisomerism, it is made up of three letters. A means not, tropes, turn, and isomers. So atropisomers are result due to restricted rotation around carbon-carbon sigma bond. So atropisomerism are the stereoisomers as a result of the restricted rotation about a single bond. It is also called axial chirality, and chirality is not simply the center or plane but an axis. Because atropisomerism is resulting due to the chirality around the axis, therefore it is called axial chirality. This atropisomerism name was given by the Kuhn in 1933. But actually this atropisomerism was detected in 1922 by Christie, and the compound was 6,6'-dinitro 2,2-diphenylic acid. And this atropisomerism generally exhibited by biphenyl and biacid. Now see why this atropisomerism is resulting. Let's have a discussion. When compounds are said to be stereoisomers of one another, it means they have the same chemical formula, same atom connectivity, but are different from one another in the way they occupy the three-dimensional space. Steric strain is a type of strain energy that is experienced by a molecule when the atoms of the molecules are brought into close proximity of one another or forced to occupy the same physical space. Now see, the atoms want to maximize space between each other. Why? To minimize any repulsive interaction. Now, normally we would expect single bond to be able to rotate freely. But in case of stereoisomers of atropisomers, it turns out that steric strain is so much that the molecules are stuck. Or locked into one specific conformation, and they don't actually rotate at all. So this is the basis of the atropisomerism. Now let's look upon the conditions for the atropisomerism, that is conditions for the optical activity. Number 1, there must be ortho-di substitution. Now question arises, how many? So there are 2 ortho positions at each phenyl nucleus, so there must be total 4 ortho substitutions. These groups must be necessarily bulky. So these are 4 substitutions, 1, 2, 3 and 4. And all the 4 substitutions are at the ortho position of each biphenyl. And these groups should not be similar, means A should not be equal to B. Otherwise they will not would be enantiomers. The configurational stability of axial chiral biaryl compound is mainly determined by 3 following factors. Number 1, a rotationally stable axis. Number 2, the combined steric demand of the substituent in the proximity of the axis. Number 3, the existence, length and the rigidity of the bridges. So these are the conditions that a molecule or that a biphenyl molecule must possess in order to exhibit the atropisomerism. Let's see how the stereochemical assignment is done for atropisomers. So in order to accomplish stereochemical assignment for atropisomers, Newman projection structure of this biphenyl nucleus is considered. The ortho, meta, substituent, meta not always, in only some cases, are first assigned priority based on the Kahn-Ingold Prelog priority rule. These rules are also known as the CIP rules that we have already encountered in case of RS nomenclature or EZ isomerism. So starting with the substituent of the highest priority in the closest ring. So there are 2 rings in biphenyl. So one nucleus or one ring is closest to the viewer. So we consider the substituent of the highest priority in that nucleus and we move towards the substituent of the highest priority in another ring. Now during this moment, if one moves clockwise, then this assignment or this configuration is assigned a P configuration. P means plus. It is also represented by this symbol. If one faces or move counterclockwise direction or anti-clockwise, then the assignment done is M or minus, and it is also represented by this symbol. So now this discussion I will take in next slide with an example. So in order to simplify the configurational assignment, let's divide this whole procedure in steps. In first step, divide the whole molecule in 2 parts. part X and part Y. Now in second step, decide which part is near to the viewer and away from the viewer. For this example, let's consider X is nearer to the viewer and Y is away from the viewer. Now, in next step, decide the priority. So here, A is having higher priority as compared to B, and A prime is having higher priority as compared to B prime. Now, the viewer has to move the portion that is in near to the viewer, that is from X to Y. During this movement, he has to move the group of the higher priority of the ring 1 to the higher priority of the ring 2. So here in this case, A and A prime are at the highest priority, and this whole assignment is to be done at the Newman projection structure. So A and B are in the close proximity to the viewer, so that's why they are represented by a dot, and since A prime and B prime are away from the viewer, they are represented by a circle. So now the viewer is moving from A to A prime and following the counterclockwise direction. So therefore, this structure will be assigned the configuration M. If viewer is moving in clockwise direction, the configuration is assigned as the symbol P. So this has shown been by example H methyl, CHO and O methyl. So in this case, the priority goes to the methyl, and in this case priority goes to the O methyl. So now this is the nucleus 1, this is the nucleus 2. Nucleus 1 is nearer to the viewer. So we can derive like this. This is a nucleus that is away from the viewer. So I am representing this structures, and this is the ring that is near to the viewer, O, ME and CHO, and here ME and H. Now see, the viewer is moving from OME to ME in counterclockwise direction. So that's why it has been assigned the M configuration. So to simplify this, let's see this here. This representation has been represented with different colors. The group that are near to the viewer are represented by blue color. The groups that are away from the viewer are represented by the green color. A movement from A to A prime is counterclockwise, so that's why the assignment is M. And in this case, the movement is from A to A prime is clockwise, so it is assigned the configuration P. Please recall, here M stands for minus and P stands for the plus. This is the position of the viewer. So from this example, it is very clear that we can assign the configuration for the atropisomers. So in next slide, there are some examples that shows atropisomers, that is binol, and 6,6 prime dinitrobiphenyl 2,2 prime dicarboxylic acid. Now we will discuss stereospecific and stereoselective reactions. So first of all, we should able to differentiate between these two reactions. Stereospecific reactions are the reaction in which stereochemistry of the reactant completely determine the stereochemistry of the product without any option. Means what product will be formed, it will totally depend on the stereochemistry of the reactant. However, a stereoselective reaction is a reaction in which there is a choice of pathway, but the product stereoisomer is formed due to its reaction pathway being more favorable than other available. So one stereoisomer is favored over the another. So here in this case, two isomers are getting formed, but one is major, another is the minor. Stereospecific reaction give a specific product from a certain reactant. A stereoselective reaction result in multiple products. Stereochemical information of the reactant is preserved, but in case of stereoselective reaction, stereochemical information of reactant is lost. That is, it is not preserved. So let's see stereospecific reaction. A stereospecific reaction is a one which when carried out with stereoisomeric starting material, please recall, from the stereoisomeric starting material gives a product from one reactant that is stereoisomer of the product of another. Stereospecific relates to the mechanism of a reaction, and the best known example is the SN2 reaction, which always proceed with inversion of the stereochemistry at the reacting center. So here we can see that SN2 reaction R is the starting material and the product is having the configuration S. Here the starting material is S and the product having the configuration R. So here in this case the reactant is determining which product is getting or not. SN1 reaction does not follow this pathway, and that means it is non-stereospecific and it is totally based on its mechanism. On the other hand, SN2 follows the stereospecific reaction pathway. It is one more example for stereospecific reaction in which we are getting E-alkene and Z-alkene. Now see how the stereochemistry of the reactant is determining the nature of the product. If you look upon this carbon, here hydrogen is inside the plane and methyl group is out of the plane. So we are getting the E-alkene. But in this case, hydrogen is out of the plane and methyl group is inside the plane. So in this case, we are getting the Z-alkene. So it is the totally the stereochemistry of the reactant that is determining the nature of the product. So if this type of reactions happens, so these types of reactions are called as stereospecific reactions. On the other hand, stereoselective reactions are the process in which one stereoisomer predominates over another when two or more products are formed. So have a look, these are the two reactants A and B. In this case, we are getting two products C and D. C is in majority, that is with 75% yield, and B is with minority, that is 25% yield. So if more than one reaction could occur between a set of reactant under the same condition, giving the product that are stereoisomers and one product form in greater amount than others, the overall reaction is called stereoselective. I am explaining it again. In stereoselective reaction, there are more than two or product, and out of these product, one is major, another is minor. So this type of situation is happening. So this reaction is considered a stereoselective reaction. But consider the condition that the product must be the stereoisomers. So this is the example of the stereoselective reaction. This OH is here, a chiral carbon atom. We are getting two products. One is trans, another is cis. And both are the stereoisomers of each other. Trans is major and cis is minor. So this reaction is called stereoselective. Stereoselective reactions can be classified in three types: enantioselective, distereoselective, and regioselective. Enantioselective reactions are stereoselective reactions in which the possible products are enantiomers, and this type of reaction is called enantioselective. Now see this example. One product is S, another product is R. So both are enantiomer of each other, and that type of reaction is called enantioselective. In distereoselective, the possible products are diastereomers of each other. Look upon this example. This product is SR, this product is RR. So both the products are diastereomers of each other. So that's why this reaction is called diastereoselective. In this example, one product is cis, another product is trans. Cis is major and trans is minor, and both are diastereomers of each other. So that's why this reaction is called distereoselective. Regioselective, if more than one reaction could occur between a set of reactant under the same condition, giving product that are constitutional isomers. Please remind what word I am using. They are constitutional isomers. And if one product is in greater amount than another, then the overall reaction is called regioselective. Here you can see in this reaction, this product is having one bromo, one methyl cyclohexane, and one bromo, 2-methyl cyclohexane. This is major and this is minor product. But both the structures are constitutional isomers of each other. So therefore this reaction is called regioselective. One more case here we can count that dehydration of this alcoholic reactant in presence of sulfuric acid is resulting in two different regioselective products. So overall, now we can summarize or sum up the stereoselective or stereospecific reaction. Stereospecific reaction, stereochemistry of the reactant determine the stereochemistry of the product. The example is in front of you. This is determining the reactant, the position, stereospecific position of the reactant is determining the what product we are going to obtain. But here we are getting both the isomers in which one is major, another is minor. Means one stereoisomer is favored over the other. So such type of situation is called stereoselective reaction, and this type of reaction is called stereospecific reaction. In stereospecific reaction, stereochemical information of the product is preserved. Means stereochemical information of the reactant is preserved. But in case of stereoselective reaction, stereochemical information of the reactant is not preserved, means it is lost. So it was the complete discussion of the unit 2nd of the pharmaceutical organic chemistry 2nd. I hope you must have learned something out of it. So thank you.